Hello once again. Thanks for joining us on yet another edition of Space Nuts, or more common than a daily breakfast. My name is Andrew Dunkley. It is great to have your company. This is a Q&A edition, and that means we only use 2 letters of the alphabet. But we also answer questions from the audience. Tony wants to know about binary planets and moons. Are there such things? Kevin asks, can light last forever? Alan wants to talk about a story that we did do not so long ago, the strongest fast radio burst ever recorded. And Rennie is back with vertical oceans. That's all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Joining us once again to unravel all of that is Professor Fred Watson, astronomer at large. Hello, Fred.
Andrew, good to see you again. What a surprise.
Yes, indeed. It's good to see you too. I actually got to see your office for real the other day.
Yeah, you
nice.
did.
Yeah.
And you couldn't believe how small it is.
That's the thing about cameras in general. They tend to make things look much, much bigger than they really are. But
well,
yes,
it's big enough. Put it
yes, it does the job. I mean, mine's probably a bit smaller than yours by the look of it.
There you go.
Yeah. Yes. Now, we should get straight to business. We've got 4 questions to tackle today, all text questions. And while I'm at it, I will send out an appeal for new questions. We're running short. We sort of threw some together the other day because we didn't have much to work with when I got back, because I had completely erased everything that I had done and left it all to you and Heidi. But now I need some stuff. So send us some questions via our website, spacenutspodcast.com or spacenuts.io, audio or text. We don't mind which. And we'll get stuck into them. Now, Fred, question 1. Hi, Fred, Andrew, and or Heidi. Love the podcast. Keep up the good work. Dad jokes and bizarre background animal noises. Congratulations on being, wait for this, Fred, congratulations on being the 7th biggest astronomical show. 7th biggest.
We were.
Woo!
Yeah. 7 out of the top 50. Yeah.
Yeah, I thought there were only 8. Anyway, carry on. Tony says, the podcast often talks about binary stars, but can planets and moons also form in a paired configuration? Could this happen, or would competing gravitational forces from larger mass objects make it impossible? I presume that as we haven't found any binary planets or moons amongst the myriad satellites in the solar system, that it's very unlikely, but is it impossible? That comes from Tony in Scotland. He's 20 minutes from St Andrews. He thought you'd like to know that.
Yeah, that's lovely. Indeed, St Andrews is right behind me on the wall. That 17th century map there.
Yes, I see that. Nice.
The answer is yes. Now, clearly, planets can form moons. We've got one, and most of the other planets, actually, Mercury and Venus don't have moons, but all the rest do. But I think that's not what Tony's asking about. It's about, the idea of things forming in pairs, like binary stars, where you've got 2 stars which might have fairly comparable masses and orbit around a common center of mass, which we call the barycenter. So, yes, objects, stars, we think actually stars form more commonly in pairs than singly, which is quite interesting because the sun doesn't have a binary companion. I think got lost a few billion years ago and we still don't know where it is. That's one of the things that people actually look for, the sun's sibling star, one that's got identical chemistry to the sun. There's a few candidates. Anyway, can planets do that? And the answer is yes. And in fact, it's not just planets, but the smaller bodies of the solar system perhaps more readily form in binaries as pairs. And the kind of classic example of this is when we look at many asteroids, not all of them, but many of them are shaped like peanuts in, a peanut shell, because they've got two lobes to them, two blobs, which are stuck together. And that's thought to be because they formed as a pair of objects and gradually spiraled together, not colliding, but in a fairly gentle coming together, where basically gravity just pulls them together and they stick together, and they often form a region around the join, if I can put it that way, where material tumbles down from the surface and collects in that area. And you've only to think of some of the best known ones, like do you remember Arakoth?
Yes.
We thought it was a snowman in the deepest depths of the solar system. It's actually two pancakes joined up, effectively, but that's a binary object. You and I spoke back in the mid 2010s, I think, about the comet known as Churyumov-Gerasimenko, otherwise known as 67P, which looked like a rubber duck. That's because it had two lobes as well, a big one and a small one. Yeah. So that two-lobe situation, very common among the smaller objects in the solar system, probably binary systems that have come together. Not only that, we know of many asteroids that have moons. And perhaps the best known, and certainly as far as space nuts is concerned, is that pair known as Didymos and Dimorphos, which are the pair of asteroids that the DART spacecraft targeted a few years ago. DART clouted Dimorphos firmly in its face at a speed of 6 kilometers per second, half-ton of material, and changed its orbit around Didymos by no fewer than 30 minutes. It was quite a successful venture. So that's all telling you that there's pairs of objects are very, very common. And I suppose the best example of what you might call a binary planet, because a binary planet, you'd expect the two masses to have roughly equal or similar characteristics. But the dwarf planet Pluto and its satellite Charon, I think Charon is half the diameter of Pluto, if I remember rightly. It's quite large compared with Pluto. And they orbit around their common center of mass, the barycenter. So the kind of informal definition of a binary object is when the center of mass of the two halves of it is outside either body, if I can put it that way. So the center of mass is somewhere in the space between them, rather than being inside, as the center of mass of the Earth and Moon is actually inside the Earth, which is why we consider the Moon to be a satellite and not really a binary object. Am I making sense there? That's basically the story. It's a very common phenomenon.
Could it work for planets the size of ours, though? Let's say Venus was out here. Could we sort of get into that kind of dance with Venus, because they're similar sized planets, similar mass?
They are, that's right. And I'm sure it's not impossible that a situation like that might arise. I suspect why it doesn't is it's linked with the way we define a planet, Andrew, because to be a planet, an object's got to have pulled itself into a spherical shape, but it's also got to have cleared all the debris around it. And that's the process of accretion. That's, gravitational sweeping up of the material within the old protoplanetary disk that used to be around the sun, but is now the planets. And so I suspect that process itself perhaps favors single objects, because anything that looks as though it's going to be another object the same size will get swept up by one or the other. There'll be one of them that turns out to be dominant. And it's possible that that's why we see the planets singly, because they're big and they've swept up the material around them. Whereas when we look at the asteroids and moons and things like that, dwarf planets like Pluto, you might find binary objects are much more common because there hasn't been that gravitational cleaning up of their environment, if I can put it that way.
Yeah.
So I suspect that's the way it works. Yeah.
That makes sense. Very good. All right. So, Tony, it's taken us 10 minutes to tell you yes.
Sorry about that, Tony.
But yes.
But great. Give my love to St Andrews.
Yes. Yes, he says he's from darkest Fife.
Well, Fife's it's probably it'll be dark soon when we get to the winter solstice in the northern hemisphere. But it is a very, very pretty part of the world. In fact, it might have been James, one of the early kings of Scotland, described it as a beggar's mantle. What was it? A beggar's mantle fringed with gold. And what he was referring to is that it's this green landscape with a lot of agriculture. So all the fields are like a beggar's scarf, which is bits of material sewn together and fringed with gold because it's got golden beaches all the way around it.
Nice. Very nice.
Yeah, it's a great place.
Yeah. Thanks, Tony. Thanks for your question. Next one comes from Kevin. Hello, I love your show, and please keep Heidi coming back even as a guest host with both of you. We're actually talking about that. The three of you would be great together. Oh, that's nice. My question is, if the universe is 13.5 or so billion years old, how long before we stop seeing the light from 13.5 billion years ago? It seems that every 20 or 30 years we launch a new telescope and it keeps being able to see further and further back. But eventually the light that's 13 billion years old will have to be 4 billion years old. The light can't keep lasting forever, can it? I hope I'm clear enough. I know they say the universe is expanding out to 46 billion light years, but we don't know for sure because we can't see beyond the cosmic microwave background. Thank you from Kevin. It's a good question. We have talked about the life of light. That's a good title for a book. The life of light before, and I think you did say it does have a termination age. Sometimes light ends where it hits something, and it turns into something else. But I can't remember. But
yeah. So actually, if it doesn't hit something, it does pretty well go on forever.
Is that true?
And it is sort of counterintuitive. We tend to think things that go on forever are something wrong with them. But it's not just light; it's electromagnetic radiation. It basically keeps going to infinity. Now, it might get very, very weak because of the inverse square rule. As the distance doubles, the intensity goes down by a factor of 4 because it's the square of the distance. But the question that Kevin poses is an interesting one. I mean, where it's absolutely true that we are seeing the flash of the Big Bang when we look at the cosmic microwave background radiation. Exactly as he says, we can't see beyond that. So we see that as a brightness of the sky in microwaves, radio waves, that is everywhere in the sky. And it's almost completely uniform. It's not quite, and it's just as well because that non-uniformity is caused by the sound waves within the Big Bang plasma, which eventually is what gave rise to galaxies and stars and all the rest of it, we think. So yes, we're looking at a boundary beyond which we can't see, and so I think just clarifying Kevin's comment, that 46 billion light years is probably what we call the proper radius of the universe. In other words, it's the radius of the universe if we could see it all, but we can't because we're always looking back in time. So we tend to talk about co-moving universe, the looking back at a time. So if we think in terms of look-back times rather than in terms of distances, that's the short answer. So our look-back time to the cosmic microwave background radiation is 13.8 billion years. But the universe probably goes on a lot further beyond that, exactly as Kevin said. So we can't really define its size. But what is interesting is that boundary, that cosmic microwave background boundary, is actually receding from us at the speed of light. I won't go into the details of why we know that, but it's moving away from us at the speed of light. But it's still, the light that it has emitted is still going on through the universe and will continue to do so. Eventually, as the universe expands, it'll get very weak, particularly if it turns out that dark energy just keeps on going. There's new evidence that suggests that dark energy is reducing, which might mean that one day there is a turnaround, and we might one day be back to the big crunch idea that we had in the 1970s, or the Gnab Gib, as Brian Schmidt calls it. So,
or the big crack.
The big crack could be, if it keeps on expanding, the big rip, where space itself just tears apart. I think that's a weird quantum phenomenon that I'm not going to get into now, but something to look forward to anyway in the distant future.
Yes. We can wait. We usually say we can't wait to examine the samples from Mars, but we can wait for the big rip or the Gnab Gib. Definitely no hurry for that. Thank you, Kevin. Lovely to hear from you. And this is Space Nuts Q&A edition with Andrew Dunkley and Professor Fred Watson. Today's episode of Space Nuts is brought to you by Insta360, the clever folks who make those mind-bending 360 cameras and action cams. And now they've gone pocket-sized with their brand new Insta360 Go Ultra. Now, when I say pocket-sized, I mean it. This thing is about the size of an Oreo. At just 53 grams, it's so light you'll forget it's even there until you see the footage. We're talking silky smooth 4K at 60 frames per second. Not bad for something that lives in your pocket. And it's not just small, it's smart. With a magnetic mounting system, you can clip it to your shirt, your hat, or even stick it on your bike, a street sign, or your fridge if you're filming an action-packed sandwich-making tutorial. The upgraded sensor means your shots look amazing day or night. It's also waterproof down to 33 feet, so you can take it swimming. Battery life? The standalone camera gives you about 70 minutes. Add the action pod and you're up to 200 minutes. And here's the kicker. With fast charging, you can go from 0 to 80% in just 12 minutes. And here's the sweetener. For the first 30 Space Nuts listeners, Insta360 is throwing in free sticky tabs so you can mount it pretty much anywhere. Jackets, backpacks, you name it. Just head to store.insta360.com. Use the code SPACENUTS and you're set. Links are in the show notes. Check it out. The Insta360 Go Ultra. Small camera, big fun.
Roger, you're loud and clear here also.
Space Nuts.
Our next question comes from Alan. He's in San Antonio, Texas. Recently, I was listening to another podcast where they talked about a news story about the strongest fast radio burst ever recorded. Yes, we have talked about that before. It's not an astronomy or science podcast, so they'll not be able to answer my question. And he thinks we can, Fred. Anyway.
We can put him right.
They mentioned that most fast radio bursts were from billions of light years away. My first thought was, hold on, if we don't know the cause of FRBs, how can anyone know the distance to the source? Hopefully Fred can answer that. Then maybe Fred will talk about the news item. If I heard right, the FRB that it was talking about is intrinsically the brightest ever, and it was in the Milky Way. If that is the case, then its apparent brightness must have been so powerful that it saturated the instruments on the telescope. That comes from Alan in Texas. Yeah, we spoke about that when it was first published, the findings first published. Yeah, the brightest ever fast radio burst or something to that effect. So we probably should talk about that first before we answer the first part of the question.
Yeah, the GOAT, wasn't it? Greatest of all time.
Yes.
Yeah. But I think we're talking about two different things because if you have the intrinsically greatest of all time within our own Milky Way, don't get fried, I think.
Whoops.
Or at least as exactly as Alan says, it would fry the instruments on the telescope. Exactly right. There certainly have been FRBs which come from our galaxy. They're thought to be flares on magnetars. A magnetar is a highly magnetic neutron star, intense magnetic fields, sort of unbelievably intense, and occasionally you get flares on these things which give you this very brief burst of radiation, which we call an FRB, a fast radio burst. But that was one that was not as powerful as the ones that we see deep in the universe, the GOATs, the greatest of all time. So I'm probably not covering that news item very well. But let me just briefly answer the first part of Alan's question. If we don't know the cause of FRBs, how can anyone know the distance to the source? It's a great question. And that was one of the puzzles in the early era of fast radio bursts. There were a lot of them were detected. They only happened once. There are a few repeating ones, but most of them only happen once. What you have to do is when you detect one of these things, you have to use a radio telescope that is capable of pinpointing its direction with very high accuracy. And that's where ASCAP came in, the Australian Square Kilometre Array Pathfinder, ASCAP, which is a telescope in Western Australia. It's an array of 36 dishes. And because it's an array like that, it's very, very good at pinpointing where signals come from to a very high degree of accuracy. So if you can do that, and it took them a while to get that act together, but they did, what you can do is then take that position and look at that point with a visible light telescope. And what was found consistently with fast radio bursts is, yes, they come from distant galaxies. The puzzle was that they're not usually in the center of these galaxies, which is where you expect all the high energy processes to take place because there's a supermassive black hole there. Yeah. Often they're in the kind of suburbs of galaxies, which is one reason why we believe they're these magnetar flares, because then they're not something associated with a high energy supermassive black hole. They're associated with very compact stars. So if you can identify it in a galaxy, then you can measure the redshift of the galaxy itself using an optical, a visible light telescope. That gives you the redshift, which we equate to distance. So that's how we know where they are and how far away they are. And that's really, one of the great stories of the FRB saga, that we have managed to pinpoint these brief flashes of radiation. They last 1,000th of a second at most, and find out where they come from. And it's just because we can pinpoint their positions very accurately and then follow it up with optical or visible light telescopes. I have to say that one of the great collaborations in that regard has been ASCAP, the Australian Square Kilometre Array Pathfinder, linking with the telescopes of the European Southern Observatory down in Chile, the optical telescopes, what we call the VLT, the very large telescope, those 4 8.2 meter telescopes that are so good at measuring the distances to very distant objects. So that's been a really great collaboration.
Mm. Now, you probably already answered this in the past, and my brain won't let me find the answer. But what causes fast radio bursts?
It's what we were saying, the idea of a flare taking place on the surface of a highly magnetized neutron star.
Right.
Now, we find that very hard to envisage, because you and I have struggled to imagine what neutron stars are like when we know that they've got mountains on them that are a few millimeters high.
Yes.
What is the surface of a neutron star like? It's just it's impossible to imagine. And so it's kind of equally impossible to imagine a flare on one of these things that is so bright that it outshines the sun for a 1,000th of a second, or outshines the sun's entire radiation history for 1,000th of a second. Amazing stuff.
Extraordinary. Thanks for the question, Alan. Hope you're well. Now let's take a break from the show to tell you about our sponsor, NordVPN. Now I think we'll all agree that exploring the universe is thrilling, but exploring the internet without protection, that's a black hole you don't want to fall into. Sorry. As a Space Nuts listener, we have an exclusive deal for you so you can stay protected, and that is NordVPN. It's the fastest, most secure way to browse the web. With NordVPN, you get next-level encryption, blazingly fast servers around the world, and zero tracking, so you can stream, shop, or scroll safely. It's the tool I personally trust when we're diving into the internet, and we want to give you peace of mind. I've used it overseas several times. I've used it at home. It works, and it is seamless. Head to nordvpn.com/spacenuts for an exclusive deal just for Space Nuts listeners. Big savings plus 4 months extra, absolutely free. Don't surf the cosmos unshielded. Secure your digital universe today with nordvpn.com/spacenuts, and don't forget their 30-day money-back guarantee. Go to nordvpn.com/spacenuts. Now back to the show.
0G, and I feel fine.
Space Nuts.
And to our final question today from one of our regular contributors. Hi, Rennie. If I look at the Earth from the distance, let's say, of Earth's moon, and Earth is in a gravitational well, why aren't the vertical oceans on Earth that I'm looking at not dripping down the sides of the Earth towards the deepest parts of the gravitational well? I'm not sure. Is it serious? Maybe he is. Some people look at the planet and go, okay, it's a sphere, so why is everything staying where it is? Why wouldn't the water drip down to the bottom? It's gravity.
I love it. A big puddle in Antarctica. Well, yes, it is in a gravitational well, but it's a three-dimensional one. We look at depictions of a gravitational well, and it's like a trampoline. It's a surface with a dent in the middle where you've got planet Earth or whatever other gravitational objects we're talking about. So a gravitational well is a good description because that's sort of what it looks like, except that it's a gravitational well in 3 dimensions, not 2 dimensions, as the surface of a trampoline is. So it's a 3-dimensional entity, and it turns out that the gravitational well is at the center of any gravitating object like the Earth. So, yes, the oceans do drip down, but they drip down towards the center of the Earth, which is where the gravitational well is, because it's a 3-dimensional well, not a 2-dimensional one.
There you go.
I do love the idea of the oceans kind of running down the side, though. It's quite nice to think about.
Be pretty weird.
Fortunately, not the way it is, because the whole thing exists in 3 dimensions, and we've got the center of the Earth as being the bottom of the gravitational well.
Indeed. Simple answer to that one, Rennie. So thanks for sending your question in. And once again, I'll appeal for new questions. If you'd like to send them in to us, jump on our website. I'll just do a search for Space Nuts Podcast on your search engine and find us there, and send us text or audio questions, which are through the AMA tab up the top. And don't forget to tell us who you are and where you're from. We always like to know that, just so that we can spam you. Yes. All right.
Is that what it's for?
No, of course not. Of course not. We only send spam to people who volunteer for it.
Yes, that's right.
Yes. Thanks, Rennie, Alan, Kevin, and Tony for your questions today. And thank you, Fred, as always. It's been great fun.
It's great to answer the questions like that, or at least have a crack at answering them. They're always thought-provoking. And thanks to all our listeners, and thanks to you, Andrew, for carrying the show forward.
Oh, my pleasure. I enjoy it. It's great fun. And we'd thank Hugh in the studio, except he didn't turn up today. He went for a swim and ended up in Antarctica. So, yes, he loves it down there. He's, He's a fun guy. And that's it from us for another week. We'll see you very soon on another edition of Space Nuts. And from me, Andrew Dunkley, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.